This presentation is focused on answering questions from viewers regarding the outstanding performance tests posted on the H2IL website. After viewing the following logical reasoning, you'll be more convinced that the self-sustaining electrolysis system is indeed producing an efficiency much greater than 1:1 or 100%. In the test series, we detailed the simple and conclusive method of testing and presented a selection from the library of recorded performance tests. These are compiled to give sufficient information for the viewer to form an independent analysis and report. They are superior to an independent report in that you get to see the processes, dynamics, and statistics, so you can draw your own conclusions. All camera views are time-stamped to eliminate trick photography and give the necessary credibility. Yes, it's as good as being there, on-site, watching a test take place. The series of tests confirm the flow rate and that the gas produced is hydrogen, which is the only combustible gas that rises upward. The MQ8 hydrogen sensor also confirmed that the gas flow in the large-scale display bubbler was hydrogen and not compressed air. The latest tests, number 4 and 5, also answered recent questions regarding possible pre-sample back pressure and overpower boost just before taking the sample. Over the next few minutes, the technician will present added reasoning to confirm that the output gas quantity is way in excess of what would be needed for just a 1:1 or 100% efficiency, verify that the input level meters are calibrated correctly, and take the viewer through a logical process to confirm the credibility of the input energy level. Let's hand it over to Dave to explain.
The gas over air collection in the test videos confirmed the output quantity, a method that reputable scientists have not disputed and that uses common-size containers that are recognized internationally. So let's consider the output gas quantity from another angle. Ask yourself how much gas would flow through the bubbler if the efficiency was only a scale of 1:1 or 100%. Well, let's first do the equations. 9,900 liters of hydrogen gas delivers some 30 kilowatts of usable energy, rounded off for simplicity. With an energy efficiency of 1:1 or 100%, it would require 30 kilowatt hours to produce 9,900 liters of hydrogen. Therefore, divide 9,900 by 30, and we conclude that 1 kilowatt hour of input energy would produce 330 liters over that 1 hour of constant runtime. Divide the 330 liters produced per hour into quantity per second, and we arrive at 92 milliliters of hydrogen produced per second from a constant 1 kilowatt input energy and a 100% efficiency. This syringe has a total volume of 85 milliliters from end to end. Holding this syringe up to the bubbler gives an idea of what just 92 milliliters of hydrogen looks like. Therefore, if the system was just 100% efficient, then the bubbler would be displaying only the quantity needed to fill this syringe over a 1-second period. The bubbles of gas located alongside the syringe would fill the syringe over 3 times per second, given also that the displayed bubbles are compressed size. Hydrogen, being 14 times less dense than air, compresses in water much more than air, so the bubbles appear smaller than the actual volume of gas inside the bubble.
What do you think? Is the system producing more than just 92 mils per second? Absolutely. It's quite obvious that the amount of gas it takes to fill the syringe is only about 5% of the complete bubbler flow.
To further confirm the gas flow in the display bubbler to be hydrogen, the technician holds the MQ8 hydrogen sensor, this time well up above the sampling pipe, which shows a rapid increase in hydrogen detected when the sample port is opened. Remember that hydrogen rapidly moves upwards. We also use this container free of any gas to demonstrate the gas is not simply air injected through the system. only hydrogen would rise and retain in the upside-down container. All other gases would rapidly drop. Upon ignition, most of the pure hydrogen gas remains in the top of the container until turned upright, causing the rising gas to burn as it mixes with air. All other gases would have dropped with gravity, leaving the container empty well before attempting ignition.
So what about the input energy part of the efficiency equation? Could the displayed meters be rigged and the power actually be way up above 30 kilowatts?
Well, let's first verify the accuracy of the amp and voltmeter displayed in the test video. Located below the cell, we have access to the main positive and negative terminals to the cell. We utilize an auto-scale multimeter that cannot be rigged and that is calibrated using this 12-volt battery. First, we verify the input volts. There will be a slight difference due to the cable resistance. However, the multimeter confirms it to be about 75 volts. To further remove any doubts, we attach this 230-volt light bulb. It emits quite dim compared to the illumination of 230 volts.
Test presentation number 5 shows a camera view of this light while a quantity test is performed. The light emitting dim, proving the power level for the given amount of gas produced to be accurate.
Next, we verify the amps with the DC clamp applied. Again, it is close. The power supply pulses to acquire the stored charge, therefore the current draw is a 50% duty cycle between 7 and 21 amps. Now for some equations. In the series of tests, we were achieving an average of 2.75 liters per second, which equates to 9,900 liters of hydrogen per hour, delivering an output energy content of about 30 kilowatts rounded off. So, in reverse, for an energy factor of 1:1, it would require a constant input power of 30,000 watts or 30 kilowatts to produce the 2.75 liters per second. Wattage is a factor of volts times amps. For example, 30 amps times 1,000 volts equals 30 kilowatts. The test videos showed the average current draw to be 15 amps. So if the input was in fact 30 kilowatts, then what would the voltage need to be? 30 kilowatts divided by 15 amps equals 2,000 volts. Well, the voltmeter is nowhere near 2,000 volts, but to verify that, we attach the 230-volt light bulb across the cell terminals. If the input voltage was 2,000 volts, it would have blown the light bulb.
Just the opposite. It barely lights up, verifying that the input is more likely 75 volts rather than 2,000 volts. Okay, you've confirmed that the voltage must be correct. Therefore, could the current draw through the system be higher than what the meter shows?
Back to our previous equation. If the input power was in fact 30,000 watts divided by 75 volts, then the current draw would be 400 amps.
Well, the clamp meter shows nowhere near 400 amps.
The cable to the cell is 60 amp cabling, which would instantly burn up with 400 amps running through it. Also, the building power box for a 400 amp installation would be huge industrial equipment, not small circuit breakers. The main breaker for this complete industrial building is only 80 amps.
These facts prove without reasonable doubt that the system is producing more energy than the energy needed to run. Even if I was to doubt the 2,000% efficiency, I would have to agree that the output is indeed much greater than the input energy.
The only factor we cannot prove through a camera is that of any hidden hydrogen tanks connected to the system and constantly supplying hydrogen at a rate of 2 liters per second for hours on end.
I think common sense tells us that no one in their right mind would go through this degree of effort in an attempt to fool major corporations with a stunt that could easily be discovered with an on-site inspection.
However, in order to guarantee that there's no external supply or tanks of hydrogen feeding through the system, H2IL will arrange a pre-travel contract for approved visitation. The guarantee covers all traveling, accommodation, and related expenditures to be reimbursed not only in full, but tripled should this be the case.
That is truly reassuring. We invite all to view the performance test videos located on this channel or the H2 Innovation Lab website, along with other presentations on this exciting breakthrough technology. If you know someone in a large corporation that might be interested in game-changing technology or energy, then we'd appreciate it if